n minus 1 there, okay, when we're working with samples. When we're working with the true population, the total population, we just use n, okay, because we've got the real number. Okay, so that's why we use degrees of freedom. Okay, so assume that I have then these heights of plants. The mean is those heights added together divided by n. The mean is 81 of the sample. Okay. I can then do the subtracting the mean from each observation. I square that to remove the negative sign. Okay, and there's an example of a case where I didn't remove or didn't square it, and you can see my deviation came down to 0. So in other words, I do the square. The sum of the squared deviations is 56. I divide by the degrees of freedom. It tells you that, and then I take the square root of it, and it will tell you the standard deviation is 2.5. Okay, so I've got a mean figure. Okay, the mean was 81.4, and I've got a value that tells me how much deviation there is around the mean. Okay, makes sense? More hands? Oi, it's going to be a long day.
I'll try. So you've got mean of 56. Mean is, what is the mean?
Now the mean here, let me jump up here. The mean here is 81.4.
Okay, the mean is 81.4, and the standard deviation.
And the observation was 78. So the difference there is what, 3.4. Squared gives me 11.56. Okay? And I do that for each of the observations. I then add them all up together. So now I've squared them, and I add them all up together, okay, and I divide it by the degrees of freedom I have. In other words, it's the total number minus 1. That then is basically the averaged square deviation. Okay. It's a mean square deviation. Yeah. I'm trying to avoid too many terms here. Okay. I then take the square root of that, okay, because this is a squared value here, okay, and that then sort of is an indication of the average deviation around the mean.
So that means in terms of numbers, 81.4 minus 6, 81.4 plus 6.
2.5 in this case. Yeah. It's the mean plus so much, plus so much. And obviously, the bigger this value here, the wider the distribution. Okay. Does that make sense?
The more variable.
And the more variation there is. Yeah. Okay. Okay. We can come back to this. Just by the way, if you're stuck on something I say, okay, you can interrupt me, or if you don't want to interrupt me, you grab me outside and you drag me by the ear into a corner, and I'll explain it to you. Okay, so if you're stuck, and I'm serious about that. Okay. Right, we can do that on frequency distributions as well. It's there. I'm not going to go into that. But basically, this is a number, okay. If the small deviation, it means something like that. If it's a big deviation, it's something like that. You can see these all have the same mean value, but the deviations are different. Okay. And that's what the standard deviation is telling you. So if I say to you, the mean height of people in this room is 6 foot with a standard deviation of 6 inches, okay, 6 inches, I've got a picture of what's happening on either side of the mean. Okay. And that's what the standard deviation is telling you. So most statistical programs will calculate it for you, so don't get too hung up about that. It is, do you understand what it's actually telling you? And it's telling you how wide the distribution is around the mean. Okay. Variance is exactly the same as the standard deviation, except that it is the value that we calculate before we square root it. Okay. And that becomes important when we do later analyses, because essentially it's taking out the negative values and that sort of thing. Okay, I don't want to spend too much time on that. I want to introduce you to another concept also related to this, and that is the coefficient of variation. The standard deviation always needs to be seen in relation to the mean. So I go and measure the whales, or the mass of whales, and the mean mass of a whale is 5,115 kilograms. And I measure enough whales if they'll let me, and I work out the standard deviation is 243 kilograms. So in other words, the mass of a whale is about 5 tons with about 250 odd kilograms on either side of that. I go and measure the mean mass of mice, and the mean mass is 789 grams, and the standard deviation is 38.9. Now it will look like the mice have a lot less standard deviation than the whales. And I want to emphasize, you need to look at your standard deviation in relation to the mean. So one of the things we can do is we can have a look at the deviation of whales, we can have a look at the deviation around the mean of mice, and I can express them as a percentage, and you'll see that the deviation is about the same on either side in terms of percentage of the mean. And it's very, very simple. I take the standard deviation divided by the mean times 100, okay, and I've got a percentage. So in other words, I can tell you that the variation is about 5% on either side of the mean. Okay. So we need to look at deviation, standard deviation in relation to the mean. In the notes here, you will see I have a note on probability, and I don't want to spend too much time on this. But one of the reasons that we work out variances, standard deviations, and so forth, is that we can compare populations and determine what the probability is that the populations are different, or the probability that my measurements are correct, and that sort of thing. And we generally in statistics work on a 95% probability. I'll spend more time on this later in the week, but basically I want to know